So in these two, I think, videos, I will show you an example of how to use visualization on discrete data in order to use see patterns. And in particular, I want to emphasize the use of colors. Uh, I want to apologize in advance to anybody who might be colorblind. Actually, my co-author Rune is very colorblind, so he has helped me with finding the best colors. But still, I know this is a challenge. But uh, for those of us who are fortunate enough to distinguish colors, this is actually a very useful tool. And of course, visualization as a general way of working is always the same idea. You have a lot of data and you want to somehow make it easily accessible in something that you can see. And in the very basic cases that we look at very often, we will have data that represents a function, and that function we will plot, maybe 3D, or maybe we have to take some sort of cut through it or something like that. But that is something that is very well known in other kinds of math. Here I want to emphasize a situation where the data is completely discrete and we still can use visualization to sort of see what's going on. So the kind of problem I have in mind is to look at uh, numbers that are square modulo a certain prime. So let me explain what's going on here. So I've made a matrix. That's why I loaded the linear algebra package. I made a matrix and filled it up with some numbers. Those numbers are given by the indices of the matrix, and this is a 15 by 15 matrix, as you can see. And as usual, up here I have the 1 comma 1 entry, the 1 comma 15, 15 comma 1, 15 comma 15. And so the way it works is that you look at the first index and you square that, and then you take the remainder or residue after you divide by the prime number given by the second entry. So this is 2, 3, 5, 7, and so on. And then, of course, I mean, if you start with doing things mod, um, so here is the n, right? So I've taken 1 modulo various primes, that's always 1. Now then I'm taking 2 square, that's 4, modulo various primes. So mod 2, this is 0, mod 3, this is 1, mod 5, this is 4, and it keeps on going. And this is how this matrix is created. And you can see that, of course, the size of this matrix is going to be an issue. I've just chosen more or less randomly 15 by 15, not to drown myself in data, but it's going to be a problem when we look at this matrix that there are values that we don't really see. I mean, you can relatively easily figure out how wide such a matrix would have to be in order to start repeating itself, like what we see here with the small numbers. But the idea for what I'm trying to do now is to just sort of go in and look at the data as restricted to what we see here. Okay, so the question that I'm mainly interested in is the question of, suppose that we fix some number and then we ask, is that number a square modulo various primes? Right, so for instance, you could look at the number 1 and you can ask, is the number 1 always a square modulo prime? And the answer, of course, is yes. And that has to do with the fact that we're finding ones, we're finding ones all the way in the first row here. But then you can ask the same with 2, for instance. So is 2 always a prime, always a square modulo primes? Well, that doesn't look as though that's the case. I mean, 2 mod 2 is 0, so that is a prime. 2 mod 3 is 2, and that's not a prime. I mean, sorry, that's not a square, because we've listed all the squares here, and we are getting to the repeated part so quickly that we have all the values here. So 2 is not a prime modulo is not a square modulo 3, simply because if we look at 0, 1, and 2, and we square them, then we get 0, 1, and 4, and mod 3, these are 0, 1, and 1. Right? So you can ask these questions, and I want to ask it more generally, and I'm particularly interested in the case of when negative numbers are primes. So for instance, I could ask the question, when is -1 a prime? And then that's going to be slightly more complicated to answer, because the situation that we have here is that there are no negative entries in this table. But of course, if I want to know if if I want to know if -1 is a prime modulo, say 17, then I have to look for the number 16, which obviously is a square, because 16 represents -1 mod 17. So this is the kind of questions that we're looking for. And I want to get some visualization going, and the way I want to do this is using the sparse matrix plot uh, uh, procedure, which is built into the plots package up here, so that's why I loaded that. And the first plot I'm making doesn't really make much sense, but I'm doing it mainly to emphasize that we have a little bit of a challenge here with some transpositions, because the way sparse matrix plot works is that it will put a black box if you have an entry which is non-zero, and a white box if you have an entry which is 0. And so you can see that the first column here, which is 1, 0, 1, 0, 1, 0, and so on, this is represented in the first row here. And that has to do with a certain convention of how you print a matrix. And I get too confused for this, so I'm going to transpose the matrix so that it's going to look like this. But actually, I still want to point out that this is not the same setting that what we have in the matrix up here. This you can see by noting down here, which is the last row of the matrix, we have 2 zeros. This has now ended up at the top. And this, of course, is the discrepancy. I mean, this is a small thing, right? But usually when we enumerate a matrix, we put the 1, 1 matrix in the top left corner. But when we plot something, we put the 0, 0 entry in the first quadrant of the plane. We put that in the bottom left corner. So this is all that's happening here, and I'm going to follow this convention here. Okay, so the zeros here just has to do with, when we find 0 as a square. In that case, I'm not so interested in. I'm mainly interested in the case of -1. So I'm now asking the question, when is -1 a square? And I'm going to do this as follows. So the idea is that if I can, of course I could program this in more complicated ways, but this is a very sort of quick and easy way of doing this. So the way I'm going to do it is I'm going to take the entry square mod prime that we looked at before, and then I'm asking, is that the same as a representative of -1? And as we just saw, the representative of -1 is the ith prime -1. So I will just subtract that. So I will subtract the ith prime, that's just the entry of the prime, and then add 1 to that. And if I get a 0 out of that, that means that I found -1 as a square. And so that gives me a white box. So the white boxes that I see here are indications that we found -1 as a square. And then you can sort of see that, okay, there's seems to be two cases. One case is where this is not a square. Of course, there's two cases. One is when it's -1 is not a square, and the other one is when -1 is a square. And of course, you need to be a little bit careful, because if you're going out to the right here and you're looking at some fairly large primes, then it's certainly possible that there might be an entry later, which would mean sort of up in the continuation of the matrix there, which gives me a white section. So, I cannot trust the values too much out to the right, but certainly there's a kind of nice behavior that we can see in the beginning. So I listed down below, I listed the primes, I put in zeros just to move things a little bit to the right so that it's easier to align these things. I mean, this is also, of course, I could program this in a nicer way, but that would take time, right? So you can see that what characterizes the numbers in which the primes in which -1 is a square. Well, there's 2, that's a good number. Then there's 3, that's a bad number. Then there's 5, that's a good number. 7 is bad, 11 is bad, 13 is good, and so on. And when you stare at this for a little while, then you say, okay, there's something about 2 that might not be so interesting, but if we look at the rest, it looks like the pattern is that the numbers that are 1 modulo 4 are good, and the numbers, sorry, is that right? No, the numbers that are, yeah, 1 number modulo 4 are good, and 1 and 3 modulo 4 are bad. So that should be the pattern that we're looking for. So let's try to see if we can visualize that. So what I'm doing here, I mean, again, this is perhaps a little bit clumsy, but the point is that this is easy. I'm making a sparse matrix plot which checks what primes are 1 modulo 4, and I will get white if they are 1 modulo 4. And then you can see I'm doing this as a 1 by 15 matrix. And maybe you would be tempted to do like this so that it looks more like a 1 by 15 matrix. But then it's going to be difficult on my screen to see what's going on. So I'll go back like this so you can now perhaps see the pattern visually. So what I'm saying is that whenever I have a prime which is 1 modulo 4, I get white, which is the white zones here, then I also get white spots up here, right? And that actually works the whole way. If I was to try this further, I would really have to increase the size of my matrix to be more careful with checking this. But I'm just trying to plant an idea of how this is working, so I won't be too careful about this. This is actually a correct statement. So if you're asking, this is something that can be proved. -1 is it's called a quadratic residue modulo a prime if that prime is 2 or if it's 1 mod 4. So this sort of primitive visualization method works well because we can sort of easily see that the things are aligned in the way that I've been suggesting. Let's try to do the same with -3. So if we do the same with -3, this pattern emerges. So I'm asking, is -3 prime, a square modulo various primes? And if you stare at this for a little while, you'll see what is relevant here is whether or not this prime is 1 modulo 3, right? So of course, except for 3, then the numbers are going to be not going to be divisible by 3. So the choices you have is 1 and 2. And it turns out that these are the ones that are useful here.